started. Right? This is only observed. This alpha decay is only observed for heavy nuclei having atomic number greater than 83 and mass number greater than 150. Okay. And as you have seen in the binding energy per nucleon curve, as you have seen in the binding energy per nucleon curve, there's a low binding energy per nucleon for heavy nuclei, especially greater than 120, right? And they are basically unstable. They can undergo fission or they can undergo alpha decay to achieve that stability. So in a alpha decay, we have a parent nuclei, atomic number Z, mass number A, is decaying to daughter nuclei I, atomic number Z minus 2, mass number A minus 4. And you have an alpha particle, right? And the release of energy in the form of kinetic energy, but most of the energy carried out by alpha particle because of its light mass. Okay, so we have seen yesterday. I told you that kinetic energy of emitted alpha particle will be A minus 4, the mass number of, this is not mass, mass number of daughter nuclei divided by mass number of parent nuclei into energy released. Okay, and since A is having a large number, right, greater than 150, in front of that 4 is nothing. That's why this number is very close to unity. That's why it is written that Q alpha in the form of, I mean, it's very tends to, this kinetic energy of emitted alpha particle is tends to energy released. Okay, but how will derive that? How this thing is coming? So before that, let me introduce that Q value. Suppose you have a reaction like X is interacting with Y, or I'll give A plus B. A nuclei is interacting with B nuclei and producing the C and D nuclei. Okay. Suppose the nuclear mass of A nuclei is Ma, for B it is Mb, and C nuclei, that nuclear mass is Mc, and for D it is Md. Also assume that kinetic energy of A nuclei is KeA, KeB for B nuclei. For C nuclei it is KeC, and for D nuclei it is KeD. This number may be 0. Suppose, for example, in many cases that this is a target and this is the incident particle and the target is at rest. So at this scenario, this number will be 0. But just I mean using symbol, how will define that Q value? But I'm saying this number, suppose in many cases in nuclear reaction that this is the B is the target and A is the incident light particle bombarding the target nuclei. So when the target is at rest, obviously the kinetic energy will be 0. But just I'm using notation for any arbitrary kinetic energy. Or suppose the binding energy of A nuclei is BeA. Okay, I'm defining here, but you know this is also really important for competitive exam. How will define? I will calculate that energy release in any nuclear reaction. So suppose the binding energy of A nuclei is BeA. For B it is BeB, and for C nuclei it is BeC. For D nuclei it is BeD. Okay. So kinetic energy you can calculate in terms of nuclear mass. You can also calculate in terms of kinetic energy. You can calculate in terms of binding energy. If you calculate the Q value or energy, Q value is nothing but energy release or absorb in the reaction. Suppose आपको मैं अभी define करता हूँ Q value, then I'll tell. So suppose this I'm calculating the Q value of this reaction. So in terms of mass, how will calculate that Q value will be nothing but mass or nuclear mass of reactant. Sum of the nuclear mass of the reactant minus sum of the nuclear mass of product. So that will be like you have a MC minus MD ka C square. So in terms of nuclear mass is the sum of the nuclear mass of reactant, and you have product C and D minus sum of the nuclear mass of the product. Okay, so every product will be, and the nuclear mass of every product will be actually subtracted from total nuclear mass of the reactant. In terms of kinetic energy, the Q value is nothing but the kinetic energy of product, that is Ke C plus Ke D minus Ke A minus Ke D. So in terms of kinetic energy, the Q value is nothing but kinetic energy of the product nuclei minus kinetic energy of the reactant nuclei. Okay. ठीक है ना? And in terms of here I'm writing in terms of binding energy, Q value is nothing but binding energy of the product, that is BE C nuclei, binding energy of C nuclei plus binding energy of D nuclei minus binding energy of A nuclei minus binding energy of B nuclei. So in terms of mass, this is nothing but nuclear mass of reactant minus product into C square. M into C square is the unit of energy. That in terms of binding, in terms of kinetic energy, it's the kinetic energy of the product minus kinetic energy of the reactant. Or in terms of binding energy, it will be the binding energy of the product minus binding energy of the reactant. So if you know any one of them quantities, like if you know mass of the all nucleus in the reaction, you can calculate Q value. If you know the kinetic energy of all nucleus in the reaction, you can calculate. Or if you know the binding energy, है ना? सारे का न्यूक्लियर मास पता है तो आप कैलकुलेट कर सकते हो, सारे का काइनेटिक एनर्जी है तब भी पता कर सकते हो, सारे का बाइंडिंग एनर्जी पता है तब भी आप निकाल सकते हो. ठीक है. नाउ व्हाट इज Q वैल्यू? Q वैल्यू इज द एनर्जी वैल्यू that will be released or absorbed in the nuclear reaction. So if you are getting Q value, like you are getting Q value of the reaction that is positive number, some positive number, it means there will be a release of energy in that nuclear reaction. There will be release of energy. If you are getting Q value in any nuclear reaction is positive, it means there will be release of energy in that nuclear reaction. Or if you are getting Q value is negative, it means there is you have to supply some energy. You have to supply some energy to make this nuclear reaction. ठीक है ना? So when there is a Q value in the nuclear reaction positive, it means there is a release of energy. Okay. Or if you are getting Q value in the nuclear reaction is negative, it means to make this process, you have to supply some energy in the form of kinetic energy of incident particle. So it's like a target as an incident particle. To make this nuclear reaction, you have to supply some energy in the form of kinetic energy of incident particle. Is this clear to all what I'm saying?
Yes, sir.
Well, so what I'm doing, because I have to calculate Q value, because I'll derive at the end, I'll derive that how that kinetic energy of alpha particle is related to Q value. So if we have to have information about that Q value, that's why I have defined that. Okay. But in details, I'll also study or I'll also teach what is Q value and related information. But here it is required, that's why I give just a brief introduction. What it is Q value, just I have defined. Okay. So now I'll define, I'll derive this. Okay. Okay. So suppose this is your parent nuclei. The nuclear mass of parent nuclei, let us assume for the sake of time, that is mt. Nuclear mass of daughter is md, and nuclear mass of alpha particle, that is m alpha. During decay, this parent nuclei is at rest, so velocity of this parent nuclei will be 0, and momentum of this parent nuclei will be 0. This parent nuclei is at rest, velocity and momentum will be 0. So after decay, what will happen? So this a daughter nuclei and alpha particle, they will not be at rest. And suppose the velocity of daughter nuclei is Vd and with momentum is Pd. And let us assume the velocity of alpha particle is V alpha and its momentum is P alpha. So decay process, this nuclei is at rest, velocity 0, momentum 0. Okay. So they are not actually at rest. They will be moving with some velocity, and they will have some corresponding linear momentum. So how will define this process? Actually, you have a parent nuclei X. Okay, it's decaying alpha particle and daughter nuclei. So how will define that? So to preserve that momentum in any nuclear process or any nuclear reaction, that linear momentum should be conserved. So this particle is at rest. So the decayed nuclei, they should move in opposite direction. So this side will that daughter nuclei will move and alpha particle will move in opposite direction. This is also important because before decay, the total momentum of the reactant is 0. So after decay, the product sum of the momentum should be 0. I can define that decay process like this. Because in any decay or any nuclear reaction, that linear momentum should be conserved. Okay. So if I apply that linear momentum conservation, so what I'll write, before decay, that momentum is 0, right? And that should be equals to sum of the linear momentum of daughter plus linear momentum of alpha particle. Right? It means P alpha, linear momentum of alpha particle will be equals to minus of linear momentum of daughter. I can see from here, daughter is moving in this direction and alpha particle is moving in the opposite direction. They have phase difference like 180 degrees, right? So that's why there's a minus sign. But their magnitude will be same. Their magnitude will be same. Their magnitude will be same. Now I'll define that Q value. So what is Q value? Just we have defined that Q value in terms of kinetic energy, that will be nothing but, or I'll use that Q alpha, because in this notation that Q alpha we have used, that is nothing but kinetic energy of product, that is like you have this particle, so that will be 1 by 2 mass of this particle into velocity of this particle, right? And then we'll have mass of alpha particle half into mass of alpha particle into velocity of alpha particle square, then 0. So Q value in terms of kinetic energy, what is the definition? Kinetic energy of the product, and product you have like daughter, its kinetic energy will be half md nuclear mass vd square velocity square, and then kinetic energy of the alpha particle, and since this parent is at rest, the kinetic energy will be 0. So this will be the Q value of this decay process. Now if you see that PD was like P alpha, right? PD was like P alpha, their magnitude same. So this reaction in terms of momentum, I can define like this: P d ka square, right? P d ka square by twice md plus P, or I'll use the same formula here, half m alpha v alpha ka square. Now in place of PD, what I'll use, I can see that PD is nothing but P alpha, and P alpha is nothing but m alpha v alpha. So this term I can write like P square by twice m, right? PD square by twice md, and I kept that term same as it is. And in place of PD, what I'll do, PD is nothing but P alpha, and P alpha is nothing but m alpha into V alpha. So here I'll substitute m alpha into V alpha. So if I substitute it, I will have 1 by twice mass of a daughter into m alpha chi square plus V alpha chi square, and then you will have half m alpha V alpha chi square. I can see that half m alpha V alpha, it will be common from both terms. If I take common, I'll have that Q value in that process, that will be half m alpha V alpha chi square. Inside bracket, you will have m alpha by md plus 1, right? This will be common, half m alpha V alpha. From here you will have m alpha by md plus 1, that will be inside bracket. And this thing is again nothing but kinetic energy of alpha particle, right? Kinetic energy of alpha particle. Okay. And this will be like m alpha plus md divided by md. The mass, right? Mass of alpha particle plus mass of daughter divided by mass of daughter. Now if you see that mass, how will define that mass? So mass is related to mass number, right? Since that proton and neutron is having almost same mass, so total, this thing we know, right? That proton, mass of a proton is same as mass of a neutron. It means mass of alpha particle, it has 2 proton and 2 neutron. So mass of alpha particle I can write like 4 times mass of a proton. 4 times mass of a proton. And similarly, mass of a daughter nuclei I can write, mass of a daughter nuclei will be कितना हो जाएगी? Tell me. How much it will be?
A-4 in mass of proton.
So mass of a daughter, you have a mass number is how much? A-4, right? So A-4 mass number into proton, that will be that will give you the mass of daughter nuclei. So mass of alpha particle 4 mp and mass of daughter nuclei will be M-4 mp. So just in place of that m alpha and md, I'll substitute these values. If you do that, you will get that energy release in alpha decay, that will be kinetic energy of alpha particle, and then you will have m alpha की जगह पे क्या लिखोगे 4 times mp and plus a minus 4, that is mass of daughter, a minus 4 into mp, and divide by you have a number that is a minus 4 into mp. I can see that mp will be common, right, from numerator and denominator, and you will have a minus 4 plus 4, that will give you a divided by a minus 4, right? So sorry, energy release in alpha decay, that will be kinetic energy of alpha particle into a divided by a minus 4. इसका मतलब क्या हुआ? Kinetic energy of emitted alpha particle, that will be energy release into a minus 4 by a. Okay. So to just to derive that, you have to remember that in a decay process, that process is happening, that parent nuclei is at rest, and that Q value is defined as kinetic energy of the product minus reactant. That product is not is at rest, but there will have some kinetic energy, and there to preserve that linear momentum, they will move in opposite direction. So their magnitude of linear momentum will be same, right? So just you define that Q value in terms of kinetic energy. Then you replace that linear momentum of daughter in terms of linear momentum of alpha particle, and you will get common kinetic energy of alpha particle from both terms. If you take common, you will get mass of daughter and mass of alpha particle. That we can write in terms of mass, their mass number, because proton and neutron is having almost same mass. So total mass of any nuclei will be nothing but mass number times mass of a proton or mass of a neutron. Just I have done that, and then I'll cancel that mp, it is common, and I'll get that kinetic energy in terms of Q value and mass number of daughter and alpha particle. Sorry, daughter and parent. Okay. Is this clear? Tell me if you have any doubt.
Yes, sir, clear.
Well, so let us solve problem, then we'll proceed further. It's also important for your exam, for any exam, not only this part, whole alpha decay is important. Well, so the problem, you have a thorium nucleus, atomic number 90, mass number 230. Decaying alpha particle and converting to daughter nuclei radium, atomic number 88, mass number 226, and you have an alpha particle. And that process, that kinetic energy, energy release in the process, that is given 500 kilo electron volt. As they ask you to calculate the kinetic energy of emitted alpha particle. See, this is 5 marks question. How much simple it is? How simple it is? Yeah, but decay process is given, Q value is given, also provided Q value. Understood now? And they ask you the kinetic energy of emitted alpha particle. It's a very simple question. It was a 5 marks question. So I'll do that. So kinetic energy of emitted alpha particle will be how much? क्या हो जाएगी बताओ?
So 500 into?
Exactly 500 into?
Into 226
Very good. Then?
upon 230.
Very good. That unit will be kilo electron volt, right? So if you do that, 491.3 kilo electron volt. So the kinetic energy carried by alpha particle for this decay. Okay. Okay. Again, same decay. Have same decay. Thorium 90 and mass number 230. is decaying to a radium, mass atomic number 88, mass number 226, and you have alpha particle. So in that process, it is provided that binding energy of thorium is given, that is on 743.7 mega electron volt. The binding energy of radium is given on 740.87 mega electron volt. Okay, and also 8788, 88, got it. And binding energy of alpha particle is given, that is 28.30 mega electron volt. ठीक है ना? These are the information that is given. So you have to calculate in that alpha decay, you have to calculate the kinetic energy of radium, that you have to calculate. Kinetic energy of radium that you have to calculate. Can you do that?
Yes, sir.
Okay, how will you do that?
से पहले क्यू अल्फा निकाल लेंगे
Okay, then
और फिर सर वो काइनेटिक एनर्जी वाला फॉर्मूला लगा के वहां पे
you have to you are going correct way. First you have to calculate Q value, that we can do binding energy of the product minus reactant. Then I can calculate that kinetic energy of alpha particle from this Q value, from mass number, right? If I can do that if I can calculate the kinetic energy of alpha particle, I can calculate the kinetic energy of this radium also, because kinetic energy of alpha particle plus kinetic energy of radium, that is nothing but total Q value. Understood what I'm saying? So you have a Q value, right? Q value is nothing but kinetic energy of alpha particle plus kinetic energy of radium, that is equals to your Q alpha. Why is it is actually Q ऐसा हो रहा है? Why I'm writing that kinetic energy plus of alpha particle plus radium, that is giving you total Q value? Tell me. Just I have defined, right, that Q value is then nothing but kinetic energy of the product minus reactant. Your that parent nuclei is at rest, so that reactant kinetic energy will be 0. So total Q value in the reaction is nothing but kinetic energy of the product, because this fellow is at rest. Is not it? हाँ ना बोल दिया करो. Are you
Yes,
not?
sir.
So first
Yes,
you
sir.
calculate that. First you calculate that. So I'll calculate that Q value in that process, Q alpha. And that will be like you have a kinetic energy of the product. So product you have like alpha particle 28.30 minus, sorry, plus 1740.88, right? And then kinetic energy of the product, this is the contribution of the binding energy of the product minus binding energy of the reactant, and that is how much? 1743 point कितना है 7, right? 7 mega electron volt. So this is the Q value. So if you calculate this Q value in this process, you will basically get 25 point
25.48.
exactly 25.48 mega electron volt. Okay. Now we can calculate, right? Now we can process for calculating the kinetic energy of emitted alpha particle, and that will be A minus 4 by A. It means the mass number of daughter, that is 226 divided by parent mass number, and that will be 230, and you will have total energy release that will be 25.48. If you calculate this, calculate karo jara, how much you are getting, check.
25.03.
Well, very good, 25.03, right? Okay. So this is the contribution of kinetic energy of alpha particle. Now I can write the total energy released in that process, that is nothing but kinetic energy of alpha particle plus kinetic energy of daughter, and that is nothing but radium, right? So I know this, I know this. I can easily calculate the kinetic energy of daughter nuclei. That will be 25.48 minus 25.03 mega electron volt. So it will be like 0.45, right? 0.45 mega electron volt. So understood, you have a total energy release that is 25.48. From this energy, that kinetic energy of emitted alpha particle is having contribution like 25.03, and daughter is having only kinetic energy that is 0.45. That's why we use that notation Q alpha, because most of the energy carried out by alpha particle. ठीक है? Okay. In alpha decay, there's a law known as Giger-Nuttall law. The law known as Giger-Nuttall law. Giger and Nuttall law. TT. So in Giger-Nuttall law, basically they relate the half-life of parent nuclei in alpha decay with the energy released in the alpha decay. So they have basically large number of experimental data for various alpha decay parent nuclei. So they have basically large number of experimental data for alpha emitter, and what they noticed that the energy release in alpha decay is related to half-life of parent nuclei, and they obtain this kind of relation. You have a log of half-life of parent nuclei, that is A plus B, then Z by square root of Q alpha, square root of Q alpha. So they have basically large number of data for alpha emitter, and what they have noticed that half-life of parent nuclei is related to the energy released in the alpha decay, and Z is what here? Z क्या है यहाँ पे?
Atomic number of the parent nuclei.
Exactly. So you have a, they didn't derive say, empirical formula. What is empirical formula? Empirical formula किसको बोलते हैं? You don't know that empirical formula? You heard about that? Empirical formula उसी को बोला जाता है जिसका कोई डेरिवेशन नहीं होती है ना, इस एक्सपेरिमेंट से मैच होती है बट देयर इज नो mathematical derivation. So empirical formula, they notice that experimental result for large number of alpha decay process and what they noticed that half-life of alpha emitter is related to the energy released, and Z is here the atomic number of parent nuclei. A and B are some constant. So I can see there's a proportional relation with half-life with atomic number, but that half-life is inversely proportional to the energy release. And there's an inverse relation, right? There's an inverse relation of half-life of parent nuclei with energy release. However, there's a proportional or proportional relation with half-life of parent nuclei with atomic number of parent nuclei. I'm not going to discuss much about this because there is no mathematical background here, just experimental result they tried to explain from this empirical formula. But yes, you have to notice that empirical formula is nothing but the formula that is matching. I mean, the result is matching with experimental result. I mean, this expression is matching with experimental result, but there is no strong mathematical derivation. Now, another important theory of alpha emitter or alpha decay, that is known as what? Gamo's theory of alpha decay. Gamo's theory of alpha decay. Gamo's theory of alpha decay. Tell me if you have any doubt, then I can proceed, because this is really important for exam point of view. Gamo's theory of alpha decay. You know that scientists or nuclear scientists first measure the kinetic energy of emitted alpha particle. The kinetic energy of emitted alpha particle they measured, and what they have noticed, how will measure the kinetic energy of alpha particle? Any idea about that? Anyone tell me? Why people not asking question? So there's a detector, you know, scintillation detector. You can measure that energy of alpha particle or any radiation. So when they're measuring that kinetic energy of emitted alpha particle, they are getting that kinetic energy of alpha particle is around, actually it is around 4 to 9 mega electron volt. The kinetic energy of emitted alpha particle is around 4 to 9 mega electron volt. However, when they are decaying, while they are decaying, alpha particle is actually facing the barrier potential, and the height of this barrier potential is around 28 mega electron volt. The alpha particle is having only energy that is from 4 to 9 mega electron volt and suffering the barrier height that is 28 mega electron volt while it is decaying. जब ये decay हो रही है from parent nuclei, it is suffering barrier potential that is 28 mega electron volt, and it's a very puzzling for nuclear scientists.
Sir,
Because according
so here barrier potential, suffering barrier potential means, can you just explain it?
I'm saying you heard about this, right? Suppose you have some potential barrier. You have some potential barrier, and suppose its height is how much? V naught. And a particle is coming from left hand side. It is having energy this much. So this particle is incident and try to cross this barrier. इसका energy कितना है? This much energy, and suffering barrier height कितना barrier height suffer कर रही है? this much, right? So barrier height is greater than the total energy of this particle. So while it is trying to cross this barrier, it is suffering how much barrier? Kitna barrier it is suffering, and it has an energy kitna hai? Energy height is this much and barrier height is this much. So according to classical mechanics, what will happen?
It cannot cross.
It cannot cross. So same thing that time when that alpha particle was observed, I mean it was discovered, that time there's a classical mechanics. And that barrier, when they measure that energy of kinetic energy of alpha particle, they got that energy, it is around 4 to 9 mega electron volt. And suffering that barrier potential, it is about 28 mega electron volt. That's a very big puzzling for nuclear scientists, because that time it was a classical mechanics, and according to classical mechanics, if a particle is having less kinetic energy or less energy as compared to barrier potential, that it cannot cross or it cannot escape, right? जब एक पार्टिकल का एनर्जी बैरियर पोटेंशियल या बैरियर हाइट से कम होती है, according to classical mechanics, it cannot escape, right? So
Yes, sir.
that was a very big puzzling for nuclear scientists. That time there is a classical mechanics, and according to classical mechanics, that alpha particle cannot emit. Alpha particle cannot emit because it has energy that is 4 to 9 mega electron volt and suffering barrier height that is 28 mega electron volt. Then later quantum mechanics came, and Gamos took the help of quantum mechanics, that is tunneling of particle or quantum tunneling. So according to quantum mechanics, Gamos took the help of quantum mechanics, and that is quantum tunneling. So according to quantum mechanics, if a particle is having less energy as compared to barrier height, and suppose the width of this barrier is from 0 to a, then there is a probability that this particle can tunnel through this barrier. This particle can tunnel through this barrier, and the tunneling probability will be how much? Kitna hoti hai? E to the power minus tunneling probability T kitna hoti hai? E to the power minus twice K into barrier width, right? And width is 0 to a means width is how much? A. And K will be how much? K kya hoti hai? Root over 2m by h cross square, and then we'll have V minus or V naught minus E. So there's a probability that this particle can tunnel through this barrier with this much probability, e to the power minus twice Ka, where A is the barrier width and K is like root over 2m by h cross square V naught minus E, where V naught is the barrier height, E is the energy carried out by this particle. And same thing, now he took this help of quantum tunneling, and what he said, he assumed, Gamos assumed that alpha particle inside nucleus or inside parent nucleus is actually not pre-exist. You can mention that Gamos said that alpha particle inside parent nucleus is not pre-exist. It's not pre-exist. It is creating and try to escape from this nuclei. If possible, then it can escape. If not, then it will combine with nucleus. Again, it will form, it will try to escape. If possible, it can escape. If not, again, it will combine. So there's a creation of alpha particle and destroying of alpha particle inside nucleus, it is happening. Suppose मान लो आपका 1000 times create हुआ है alpha particle, 1000 में से एक बार emit हो रहा है और 99 times fail हो रहा है ना? जब fail हो रहे हैं क्या हो रहा है? Again it is recombined with nucleus, again it is creating, this kind of thing is happening. He assumed that He assumed that it is creating is not actually pre-exist, it is creating, it's trying to escape from nucleus. If success is fine, if it is not possible, it is again combined with nucleus, again it is creating, again it is destroying. This kind of thing is happening, he assumed that. Now if I draw that barrier potential inside nucleus, how it will look like? I draw that barrier potential inside nucleus. You understood what I am saying?
Sir,
So, yes.
sir,
Yes.
this barrier is coming due to nuclear force only, right?
Exactly, exactly.
Okay, sir.
Now I'll draw that barrier potential inside nucleus. Then it will be fine. So barrier is coming due to that nuclear force, right? Not only nuclear force, there are basically two force, you know. There are basically two force. That one is basically called what? Nuclear force, and that is basically called what? Tell me. Coulomb force is also there, right? No.
Okay, sir. But sir, Coulomb is out electron proton. No?
Coulomb is electron proton. Who said electron proton only?
Oh, attract. Yes, sir, yes, sir. Understand. Proton. Yes, sir.
So you have a, if I draw that potential energy inside nucleus, it will look like this. So this is your V, huh? And this barrier height is around. So the barrier height I'll denote by V, and this is around 28 mega electron volt, 28 MeV. Huh? You can you write that unit also here, 28 mega electron volt. The barrier height, huh? So 0 is the 0, and this is equals to R. This is the barrier potential or potential energy inside nucleus. Huh? And then there is a this kind of decay. Huh? I expect there will be many questions from here. If not, then it will be very sad. So I have a potential energy or potential barrier inside nucleus is like that. At 0, it is, I mean, attractive potential up to R. And beyond R, there is a sudden Coulombic repulsion. And you have a energy of alpha particle is only this much. ये height आपका कितना है? That is 28 mega electron volt, and the energy of alpha particle is only this much. I can represent that energy is almost equals to Q alpha, because you know the total energy released is almost equals to the kinetic energy of emitted alpha particle. Okay, so this is the energy of alpha particle, and this is the barrier height is facing while escaping from nucleus. So according to classical mechanics, particle having energy this much it cannot escape this much barrier height, because barrier height is higher than its total energy. So I have represented the total energy of alpha particle is Q alpha, because Q alpha is almost tends to kinetic energy of alpha particle. But according to classical mechanics, quantum mechanics, that particle can have wave nature, right? And that wave can tunnel through this barrier with certain probability. That you have learned in quantum mechanics, right? This much is the energy and this is the barrier height. Quantum mechanically it can tunnel that barrier and it can escape from that nucleus. And this point, यहाँ पे क्या हो रही है आपका basically? The point B is the point B where kinetic energy or total kinetic energy of alpha particle is matching with the potential energy. और यहाँ पे potential energy क्या होगी बताओ? ये आपका तो न्यूक्लियस देखो, ये जो केस है that is inside the nucleus, that is inside the nucleus. This nature is arising because of because of Coulombic potential. Because you know that nuclear force can act only in femtometer distance. जैसे उन लोगों ने escape किया डॉटर न्यूक्लियाई और एंड अल्फा पार्टिकल थोड़ा सा दूर चला गया है ना, then there will be no nuclear force, only there will be Coulombic force, because nuclear force can act only in the distance of up to 2.5 femtometer. ये जो नेचर है ना, ये नेचर that is arising because of Coulombic repulsion, and that is, if I define that Coulombic repulsion, V at R, that will be Z minus 2 into 2 E square by 4 pi epsilon naught. So at point B, I can see that kinetic energy of alpha particle is matching with this Coulombic energy. Now I'll define what is R, है ना. तो यहाँ पे बहुत सारी चीज है आपको समझना चाहिए, है ना. First of all, you see what is R. If I ask you what is R, what is R here? No idea.
Radius of nucleus.
No, R is not like this. You have this kind of scenario, like
जो लेंथ होती है पोटेंशियल बैरियर की,
I'll tell you. XZ decaying to Y Z minus 2 M minus 4, and then you'll have alpha particle, right? Then you'll have alpha particle. So what is R? R is like you have a daughter nucleus and you have a alpha particle. So this is your daughter Y and this is your alpha particle. So R is the distance from the center to center of daughter and alpha particle. And this is the case just before leaving to each other, है ना. उन दोनों का just surface touch हुआ है, मतलब अब इन दोनों क्या हो रहा है, they just in the situation they will separate each other, and that is actually R. तो जैसे सेपरेट हो जाएगी आपका, है ना, ये तो R क्या है, एक्सट्रीम केस है, दे आर जस्ट इन द फ्लाइट मोड, मतलब अब सेपरेट हो जाएगी. अब जैसे सेपरेट हो जाएगी तो यहाँ पे आप क्या है, न्यूक्लियर फोर्स तो काम नहीं करेगी, आपका क्या काम करेगी, न्यूक्लियर फोर्स तो आप तो नहीं काम करेगी ना, आपका वो कूलम्बिक फोर्स काम करेगी. तो दैट्स व्हाई आई सेड when I'll draw this you will have many questions, but you people are not asking questions. That's a very sad actually. So inside you can see there is a attractive potential, but just when they're just leaving, there'll be high Coulombic repulsion, and alpha particle has to cross this barrier. So at point B, there will no longer be any nuclear potential, rather there will be Coulombic potential at point B. B means what here? B means that nuclear separation between daughter and alpha particle is what? B क्या represent कर रही है आपका, separation between center to center daughter and alpha particle, that will be B. R means what? Separation between center to center when they are in touch, है ना, दोनों का surface जब touch है. So can I write from here? Can I write that R will be nothing but R naught mass number of daughter की power a by 3 plus R naught mass number alpha particle, because this is nothing but the radius of daughter nuclei, and radius I can represent in terms of mass number plus radius of alpha particle, and that I can write because they are just in touch, है ना. So that is your R, is not it? So you'll have like R naught AD की power 1 by 3, है ना. AD क्या है यहाँ पे, mass number of daughter, and that is a minus 4 actually, and then you'll have a alpha. A alpha means a alpha कितना है, tell me, a alpha कितना है, 4.
सर ये जो बी है ये विदाउट इंटरेक्शन है,
हाँ जी,
डिस्टेंस बिटवीन डॉटर एंड अल्फा विदाउट इंटरेक्शन, डिस्टेंस।
कौन सा इंटरेक्शन होगी यहाँ पे बताओ? ये जो आपका क्या केस है? सपोज यू हैव अ केस लाइक दिस, यू हैव अ डॉटर
जब
हियर,
इन टच,
नो नो नो, यू हैव अ डॉटर हियर, यहाँ तक टच में है। अब
हाँ
जैसे
ये तो आर हो गई।
ग्रेटर देन आर हो गया तो फिर क्या केस है आप बताओ? इस तरह की केस है, यू हैव अल्फा पार्टिकल एंड दिस डिस्टेंस इज योर बी।
हाँ यही कह रहा था मैं, विदाउट इंटरेक्शन।
एग्जैक्टली।
ठीक है सर।
So without interaction means what? There's a Coulomb interaction here. I cannot say without interaction. There's no nuclear interaction is here, but there will be Coulomb interaction because Coulomb interaction will act up to infinite distance.
ओके सर।
Okay. So shall I stop here or I'll proceed? Tell me. I think we should stop here. We'll proceed further tomorrow, but it's interesting, huh? There will be question from here. Okay. See you. Huh?
Okay, thank you, sir.
Thank you, sir.